to speak. It'll shaping up as a great workshop as always. Okay, so I'm going to be talking about the alchemical transfer method. I want to start with explaining why it exists, what is the design principles, and the goods and the bads. And I'll talk about some application, absolute and relative binding free energies, some recent work on binding selectivity, and RBFE for protein-protein complexes. And this is not my work. I'll say a few words about the fact that this method supports advanced force fields. I don't think I'm going to get to implementations because we're running out of time. Okay. So one thing I want to mention is that, of course, there are lots and lots of free energy methods, even talking about drug discovery. The way I like to think about it is that all these methods come from a single statistical mechanics theory. So when we compare methods, and the first thing we ask, do they give the same answer? The first question one should ask is, do they reflect the same theory? If they don't, then it's two different numbers. And we're working with Tony May for a second version of the chemistry paper on the Living Journal of Computational Chemistry, of course, with the help of David Mobley also. And I hope it's going to do a little bit of this connecting. David talked about separate topology. I like to think of alchemical transfer as separate topologies. I don't know if that's accurate, but with as a coordinate transformation. So one way to think about it, why alchemical transfer exists, it was an effort to remove some of the complexity of free energy calculation done in drug discovery. There is a zoo of things that people have to learn. Chemical topologies, atom mapping, core, variable, soft core, alchemical schedule. Well, we fix that. And then the calculation is done in multiple legs. There is solvation and receptor legs. Some methods have van der Waals and electrostatic legs. It's a lot of stuff. Usually, ENG modules in MD codes only support fixed charge force fields. So you have to learn about what's supported, what's not supported. And some transformations are difficult to do. There are different estimators. So there is a lot of baggage. And we were asking the question, and it's not a new question, is there a simpler way? It's something that's easy to implement so people can get to it more easily, but it's still applicable to computer drug discovery, to computer-aided drug discovery. So it's not a toy. It's also as close as possible to standard molecular mechanics and molecular dynamics practices. For example, we want to use chemical topology. It can cover most application with minimal changes. We want a broad coverage of force fields, potential energy functions. It's easy to automate for large deployments. And something that's not necessarily the super most efficient way to do it, but still useful. It's not as fast as commercial codes, but it's still usable so that you can actually get useful stuff to it. All right, so just in one slide, what alchemical transfer is. It's alchemical, meaning that it uses an alchemical potential. So there's a lambda that merges between two Hamiltonians, two potential energy functions. For absolute binding free energy calculation, U0 will be the potential when the ligand is separated from the receptor. U1 is when the ligand interacts with the receptor. But how do you actually do it? The perturbed potential is obtained from the reference potential by a coordinate transformation. So in the case of absolute binding, we literally calculate the energy when the ligand is outside the receptor. And then there is a teletransportation. People who know Star Trek. There's a coordinate transformation that takes the ligand into the receptor. And that leads to a different energy. The difference is called the perturbation energy. In the case of binding, it's called the binding energy. And then there is a Boltzmann averaging of that advanced. Of course, we don't do advanced, but something more advanced. But basically, that's what it is. And there are a few tricks to make this work. But this is basically what it is. The reason that's easy to implement is because when you put this in an MD code, you only play with coordinates. And MD codes are very good at handling changes in coordinates. If you want to change a charge, you want to change a force field parameter, you have to do extra work. But if you just change the coordinates, things turn out to be a lot easier. And the main paper came out a couple of years ago. All right. So the advantages is that this coordinate transformation can be encapsulated and used to implement absolute when we move the ligand into the receptor binding site, relative when we have two ligands, one bound to the receptor and the other in solution, and they switch places. That's also a coordinate transformation. And we also study selectivity by moving a ligand from one receptor to another. I hope to have time to talk about that. Everything happens in one solvent box. You don't have to do multiple simulations. It's just one calculation, like MD. Of course, it's multiple MDs because there is a molecular dynamics thread for each lambda state, but it's parallel MD. It uses standard chemical topologies to do anything with topologies. The setup is as any other MD application, and it's dual topology, what we call dual topology. So it applies to scaffold hopping, charge changing without corrections. It does not use software pair potentials. So you don't have to mess around with the energy routines of the MD code. All you have to do, teach the MD code is to recalculate the energy twice. It doesn't do van der Waals electrolyte splitting. It uses unmodified energy routines. We implemented this in OpenMM. And I think this is the most important aspect. It's force field agnostic. It really doesn't care what energy model one uses. Whatever you give it, it recalculates the energy twice. So you can use implicit solvent models, you can use polarizable potentials, and I hope this is going to grow. Gianni De Fabrizi's applied with neural network potentials, but we use it also with implicit solvent. Of course, it supports PME, particle meshing, and it's fully open source. There are two, at least in our implementation, there are two pieces. There is a force called ATM force in OpenMM, and this is professionally done with the help of Peter Eastman. And then there is like a middleware. Ours is called Atom. Cyrans called Femto, but it's used to manage the calculation. So they're also bad. The main bad is that it's slower because you recalculate the energy twice, energy and forces twice at each MD step. Whether that's actually the fact that the free energy calculation is direct. There is no, you don't take differences. May actually make it converge faster. Nobody tested. So we don't know if it's actually a bad. But of course, you would like to go faster. But the fact that you need to recalculate the energy twice is certainly a bad. But okay. So this is typically what one sees in an ATM calculation. This is a relative binding free energy calculation, an animation. So there is a ligand that starts in solution, a ligand that starts bound, and during the alchemical process, they switch places. Of course, this is done with rapid exchange, so that this happens dynamically. And so effectively, each ligand is simultaneously in the solvent and in the binding site, depending on what the alchemical state is. So you can have a state in which both ligands are in both places at 50% weight, which is strange thing. That's what happens. Okay, so we have, at least in our implementation, we have a GitHub site, a website with documentation. Anybody can go there, download it, install it, run it. We have examples, tutorials, which add more time to take care of these tutorials. It takes some effort to just keep them up to date and stuff, but we do our best. So in terms of standard RBFE calculation, what we call standard, the method has been tested in the past 2 years or so. One PO tested for membrane-bound receptors. We did work with Sivant, with Eric Chen on the other Merck. So now this Merck, I call it George's Merck. One day it will be yours. But this is the other Merck. In the last free energy workshop, we pointed. I'm making this worse. I realize this. Yeah, on a large data set, Schindler et al. Accelera also tested ATM, their implementation of ATM on a fairly large data set. And in my mind, that's it. We benchmark it, it works. So we don't do any more benchmarking for RBFEs. Of course, that doesn't mean we solve the problem. There are always, in application, there are always, one thing is a benchmark, one thing is to discover a drug. Not the same thing. Okay. So I mentioned that one thing that I think is going to really take off is the fact that ATM supports advanced force field, many body force fields, in which parameter interpolation, alchemical procedure are not so easy to do. So this is, for example, an effort by Accelera to do relative binding free energy calculation with neural network potential. But we want to get into polarizable force fields. We're already doing working with Sandbox with implicit solvent models. But this is exciting. Basically, you can use whatever force field you want. So we work on accelerated sampling. We don't like to, the philosophy is not to change the MD structure, the structure of the MD code that runs the calculation. We don't change energy routines. So in terms of accelerated sampling, we mostly play around with meta dynamics on, in this case, torsional degrees of freedom. And we noticed in this paper that it makes convergence. It was particularly helpful when the ligand reorganizes in going from solution to the binding site. But of course, there are many cases where metadynamics on torsional degrees of freedom or other degrees of freedom would be useful. Methylene is nice because it's just an add-on, and so it can be plugged in very easily. And unbiasing is very straightforward. Yes, so we started playing with receptor, this idea of making a ligand hop from one receptor to another. That turns out to be very difficult. But what is a protocol that turned out to be very useful is when we have two ligands in two receptors and they swap places. It turns out the free energy of that process gives you the ratio of selectivity of the two ligands, the ratio of selectivity coefficient. So basically what it tells you, you make a change to the ligand and you wonder, how much does the selectivity change with respect to the, for example, your target and an off target? And this particular swapping, called ligand swapping, it's turning out to be very it converges quite quickly if the two receptors are not that different in terms of structure, basically because it bypasses the solvated state of the ligand and the receptor. So it's very convenient. And we benchmark, make sure that you can do thermodynamic cycles, that you can take difference of RBFEs, or difference of ABFEs, and do swapping, you should get the same answer. And we do on simple systems. More recently, with the help of Binching Wei at Genentech, we are trying to assess how useful this is for actual medicinal applications. They gave us a data set from oldish paper. And the effort here was to make ligands that were selective for TYK2 as opposed to JAK2. And it's not bad, not bad. There are challenges, and this is one of the best cases. The challenge is mostly about conformational sampling. So if two receptors are too different, so that the poses are different, it's very hard. It takes time to converge. Even more recently, we started playing with this idea of coordinate swapping, because one bottleneck of this ATM is its dual topology, meaning that if you switch the position of two ligands, then the complexity of the calculation scales as the size of the ligand, as opposed to the transformation. But we developed another kind of coordinate, which is swapping coordinates between atoms. You say, well, that doesn't change anything. Well, except that if a group is different and you transfer the group, you want to keep the ligand together, you can do coordinate swapping plus displacement of the variable group. And basically, you have a single topology implementation of this. And we tested this. It seems to improve convergence for congeneric sets. But what is really nice is that now we can do mutation of side chain. So we can do RBFEs between proteins. And we've done it with peptides. And this is a data set from Schrödinger, where we actually do RBFE between proteins. And it's okay. These are extremely difficult calculations because the sampling is difficult. So by no means the problem solved, but it runs and you get a number. And there is some correlation. Oh, against. Well, it's hard, but it's the start. I wanted to mention this because this is an undergrad research program. This undergrad, Cassandra, undergraduate, run our code to optimize peptide binding to EZH2 for cancer research. And she said, I did the calculation. What, you're sure? Because protein-protein RBFE is pretty advanced. But, and last thing, we're revisiting ABFE calculation by what we call it progressive. It's not any idea. You do, let's say you want the ABFE of humongous ligand. These are the miriatic compounds of KRAS G12D. And you do ABFE of a fragment, and then you do a series of RBFE to build up the big ligand. And kind of works. With Eric, we're testing this on a variety of systems. We get much better convergence if one were to do the ABFE of the large ligand directly, as many other people have observed, and there will be talks about it. ABFEs tend to be not very accurate compared to, say, experimental. That's for many reasons, but at least now we have a protocol that we can play. All right, so I wanted to acknowledge our direct collab, my group, the people who did the work. So Mas and Joe, who just graduated, Shinam, who may be in the audience, contributed. She's a Sandbox, and Rajat, also in the audience. And I want to just acknowledge Peter Eastman is they should make him saint or Pope. He could be Pope. Is the main developer of OpenMM, helped us a lot. Of course, Eric Chen, Gianni, I mentioned, Binching at Genentech, Woody at Cyvant and his team, and Andrea Bortolata at Sandbox. And I want to acknowledge also federal funding, who knows when that. All right, thank you. It's not easy, and it's easy to make it fail. It's in our, we don't have a lot of experience yet, but it's what you would expect. If the binding poses are very different, so if the receptor configuration and the way the ligand binds to the receptor is different between the two ligands, you will have to run forever to converge the fringe. And then there are this biology. I think we have ligands that change protonation state in going from one receptor to another. I think that's more common than one will think, especially if there is a charged side chain in one receptor and a neutral side chain in the other. So by no means this is a solved problem, but it's an algorithm that one can work with. So the example I showed for TYK2 and JAK2 is well known. The sequence similarity in the binding pocket is not, they're quite different. But geometrically, the binding site is not that different. And that seems to be doable. Binching gave us the I3K and other best cases from their portfolio. And most of them are tough, difficult.